find myself strongly disapproving of drivers who are checking their smartphones while I'm trying to jaywalk with a cup of coffee from Wawa. They should watch out for me. I'm trying not to spill. Frankly, I'm looking forward to autonomous vehicles. Robot cars will have to have hardwired into them fail-safes that make them slam on the brakes if a pedestrian steps out into traffic. If you're riding in an autonomous vehicle, you should probably use a sippy cup for your coffee. I'm Professor Mark Hinders. I'm here in the NDE lab at the Applied Science Department at William&Mary with a couple of our robots. This one's named William, this one's named Mary. We built these robots back in the days when BattleBots was on Comedy Central. My wife wouldn't let us put weapons on them, so instead we've loaded them down with sensors. We had realized, 20 years ago or so, that the kind of things that we know how to do in NDE, automatically interpreting various kinds of sensors and imagers, was one of the missing pieces in autonomous vehicles. If you're going to have a robot drive itself, it's going to have to have sensors on it and onboard intelligence so that it can understand what's happening around us. So one of our engineers built a couple of robots for us. We started loading them down with different kinds of sensors, and we took them out and about into the world to see which of these sensors might be useful for autonomous vehicles. So we've been doing ultrasound for decades, and we took a 50 kilohertz ultrasound system that we built together. Here's a 50 kilohertz ultrasound transducer cut open. There's the crystal that vibrates when you hit it with the voltage, little impedance matching layer, backing layer. And what this does is this transmits an ultrasound signal, 50 kilohertz, which is the frequency range that bats use to echolocate. It reflects back from whatever's out there, comes back and is recorded, converted back to an electrical signal fed to the computer. Okay? So the scanner that's down here on William is designed to scan both this way and that way. So if there's an object out in front of it, William can scan it, record the backscatter, and then the idea is to figure out what about the physics of that interaction of the ultrasound with the object allows you to tell what that object is. So for example, you can say to your phone or your robot, go down to the big tree, turn left. When you get to the big tree, turn left, go down to the brick wall, pick up the thing I left there, come back to me, hurry up. The hard part about that is the middle piece, which is what is it that you mean by big tree or brick wall or something like that. Okay. Especially if it's night or other bad visibility conditions. For a robot down like this, the trunk of a tree or a light pole might look very much the same. And so what we found when we went out and we scanned a bunch of trees, big trees, little trees, light posts, is that as the ultrasound beam swept across it, because the wavelength at 50 kilohertz is about like this, the backscatter of the ultrasound as the beam swept across it depended pretty strongly on the surface texture. So the rough bark of a big tree was different than the smooth bark of a small tree, which is different from a light post. And collecting a bunch of data this way, processing the data offline, allowed us to develop the rules that could use ultrasound to distinguish a big tree from a small tree. In modern language, this is machine learning and feature detection, supervised learning. We also went out and scanned a bunch of fences and walls and things like that. And what we found is, of course, a brick wall has a different backscatter as a function of angle compared to, say, a hedge or a picket fence or things like that. Then we built Mary, and Mary's a little fancier, has a fancier paint job, put a custom suspension on there. And if you can kind of look inside of here, down inside the little locker pointed up and then reflecting off the mirror is an infrared camera. So infrared cameras see heat. These cameras used to cost as much as my house. And some years ago, the infrared camera price fell below my sole source paperwork agony threshold, which was $5,000. So we bought one, put it on the robot Mary, and took Mary out and about to see what the world looked like in the long-wave infrared. It's passive imaging, so in this context, a squirrel is an enormous thermal signature. What we're looking at is how different objects in the environment took up the heat of the day from the sun and then gave it back up at night because of the different surface properties and the different conductivities, thermal conductivities of different materials, metals, wood, stone, and things like that. We found that the infrared was useful in a complementary way to the ultrasound to distinguish different objects. So again, we went out and about over the course of about a year and collected an enormous amount of infrared data from a variety of different objects. Again, small scale sorts of things, trees, hedges, fences, walls, and so on. And then we did sort of brute force machine learning feature selection on that. A graduate student at the time, Bill, happened to be an Army Lieutenant Colonel, so he could get access to the Army's largest supercomputer to grind an enormous amount of data through it to figure out what features in the infrared data were useful for distinguishing different objects. And Bill's dissertation was published in this book about 10 years ago. We did some other things. You might see on the top of here a couple of coffee cans. We built a coffee can radar just because we could. This thing that's here is an interesting device. It's called a parametric array. It cost about $2,000 back in the day. And what this does is it broadcasts, again, a 50 kilohertz signal like we were doing on William. But this 50 kilohertz signal is also overlaid with another signal that's just a little bit different, say, I don't know, 51 kilohertz. And what happens is nonlinear effects in the air as the beam propagates give you both the sum and the difference frequency. The sum, 50 plus 51, is 101 kilohertz. That high frequency tends to attenuate pretty strongly. The difference frequency, 51 minus 50, so there's 1 kilohertz. That's in the audio range, and that propagates beautifully, and it's as directional as the original ultrasound frequency. And so, what we're doing here is propagating an audible chirp a good long distance, and then looking at the reflections that come back. Here we're picking them up with just a Kinect controller. It's got excellent microphones on it, also has a camera and near infrared and other sorts of things. And what we're doing with this device is we propagate a signal something like 50 meters down a road, pick up the reflections that come back, analyze those to distinguish different classes of vehicles that are heading toward us. So it's a straight machine learning application. The idea is, if you're a small robot like this running an errand for me, you have to make sure that you don't get yourself run over when you're crossing the street. And telling what kinds of vehicles are coming towards you is a pretty important skill for such an object. And so this work involved a combination of machine learning with an extensive data set that we collected on a near campus, as well as supercomputer simulations that helped us to understand the complicated interaction of the acoustic beam with objects. So that's what we're doing in robotics. It's a combination of collecting data, simulating to try to understand what that data might mean, and then, of course, machine learning to extract features from the data that can be useful to tell different kinds of vehicles or different kinds of objects. Robots, if they're going to be autonomous, they have to know what's happening around them. They have to figure that out on their own. They have to not run me over. They have to not get run over. We'll put links to our robotics research and other related things on our webpage. Feel free to look us up there. Applied Science Department at William&Mary, as.wm.edu. I'm Professor Mark Hinders, and this is the Crimdale Bridge.